Welcome, Nocturnal Minds, aboard. Your learning journey starts now. Continuing from our previous discussion on the structure and evolution of scientific theories, let's now explore a fascinating tool often employed in their development: thought experiments. Think of them as mental simulations, running scenarios in our heads to figure things out. We've all heard of the classics: Galileo dropping balls, Einstein pondering elevators, Schrödinger's poor cat. These aren't just academic curiosities. They've genuinely shaped our understanding of the universe. The core idea is simple: set up a scenario, let it play out mentally, observe what happens, and draw conclusions. It's like doing an experiment, but with your brain instead of lab equipment. Interestingly, despite their importance, there's no single universally agreed upon definition. Some, including the author we're drawing from, suggest we might be better off diving straight into examples rather than getting bogged down in definitions. After all, sometimes seeing is believing, or in this case, thinking is understanding. So, what makes something a thought experiment beyond just being a hypothetical scenario? It's got to have more than just if X then Y reasoning. There needs to be an experiential element, something that feels like an observation, even if it's purely mental. This is what gives them that experimental ring. Imagine watching a movie versus just reading a script. The movie has that visual, experiential quality. That's the kind of feel we're looking for. And crucially, the big question isn't whether we could actually build the machine or go to the place. Think about Steven's frictionless plane. We know we can't make a perfectly frictionless surface in reality. Or consider Einstein imagining himself riding alongside a light beam. These are impossible in practice. The magic lies in the idea that we can still learn something profound just by thinking through these impossible or highly idealized scenarios. The possibility of a real-world counterpart is secondary to the epistemic power of the thought process itself. Let's look at a classic example championed by Ernst Mach, based on Simon Stevin's work. Picture a chain draped over two inclined planes, as shown in Figure 30.1a. Now, ask yourself, which way will it start to move? Before you even think about physics, your gut reaction probably says it won't move at all, right? It looks balanced. Now, imagine adding a few extra links to one side, as in Figure 30.1b. Suddenly, the outcome seems obvious. The heavier side pulls it down. But here's the kicker. The original setup must have been in equilibrium. Why? Because if it wasn't, if it started accelerating, we could keep harvesting energy from it forever. That's a perpetual motion machine. And as Mach puts it, our instinctive knowledge screams nope. We don't need to build this ridiculously frictionless setup in a lab. The thought experiment itself, relying on our intuitive grasp of basic physical principles and the impossibility of perpetual motion, delivers the conclusion. It's compelling purely through reasoning. Here's another gem, dating back to Lucretius, tackling the age-old question: is space infinite? He starts with a bold assumption: suppose there is an edge to the universe. Okay, now, throw a spear at this supposed boundary. What happens? If the spear just flies through, well, then it wasn't really a boundary, was it? But what if it bounces back? Then there must be something beyond that edge, maybe a cosmic wall or whatever stops the spear. And if there's a wall, that wall is part of space, meaning space extends beyond the edge we initially thought. So either way, Lucretius concludes, space can't have an edge, it must be infinite. This really captures those features we talked about. Visualize the spear, perform the action, see the result, draw the conclusion. It's neat, but also shows they weren't infallible. We've since learned about topology. Think of a circle, you never hit an edge while moving along it, yet it's finite. Our space might be a Sunday version of that, finite but unbounded. So Lucretius' argument, while clever, doesn't settle the question definitively based on our current understanding. Now for arguably the most famous thought experiment of all time, Galileo's demonstration that all bodies fall at the same rate, directly challenging Aristotle. Aristotle said heavy things fall faster than light things, greater than L. Galileo's setup is beautifully simple and devastatingly effective. Imagine a heavy cannonball and a light musket ball. Now, what happens if you tie them together to form a compound object plus? Well, According to Aristotle, the combined objects plus should fall faster than the cannonball alone, because it's heavier. Makes sense so far, but wait. The light part is now attached to the heavy part. Doesn't the light part act like a drag, slowing the whole thing down compared to the cannonball alone? So, H plus L should fall slower than he. Hold on. We just derived that plus lies both faster and slower than ha. Contradiction. Boom. Aristotle's theory is toast, and the beauty is, the only consistent answer left is that they all fall at the same speed. H equals L equals H plus L. Elegant, isn't it? Just pure logic dismantling an entrenched belief. Okay, so we've seen some examples. How do we categorize them? One major way is by function. First up, negative or destructive thought experiments. These are the intellectual wrecking balls. Their job is to knock down existing theories, usually by showing them to lead to absurd conclusions, a classic reductio ad absurdum. We can split these into two types. The first type targets internal contradictions. Think back to Galileo again. His first step wasn't just questioning Aristotle. He showed that Aristotle's own rules, when applied consistently, led to a direct contradiction. The theory was internally incoherent. The second type is more about violating common sense or intuition. A prime example is Schrödinger's cat. Quantum mechanics allows particles to be in superpositions, like spinning both clockwise and counterclockwise at once. But applying that to a macroscopic object like a cat, whose state depends on a quantum event, leads to the bizarre conclusion that the cat is simultaneously alive and dead until observed. It's not a strict logical contradiction, but it's deeply counterintuitive, violating our basic expectations about the world. It highlights a potential problem with extending a theory from the micro to the macro scale. Now for the other side of the coin, positive or constructive thought experiments. These aim to build up, support, or clarify theories. There are two main flavors here. The first is pedagogical or illustrative. These aren't necessarily groundbreaking discoveries themselves, but they're fantastic teaching tools. They help us visualize and understand complex ideas. Newton's cannonball is a perfect example. He already understood the physics of projectile motion and why the moon orbits Earth. But his diagram of firing cannons from a mountaintop progressively faster until the cannonball circles the Earth made it crystal clear to everyone else. You see how gravity constantly pulls the projectile towards the Earth's center, and how increasing speed makes the curvature of the fall match the curvature of the Earth. It's not just learning a fact, it's grasping the underlying mechanism. The second subclass is much more ambitious, establishing a new theory. Here, the thought experiment is meant to provide evidence for a novel theoretical claim. Newton's bucket experiment is the quintessential example here, though its historical context is a bit more tangled than the simplified story often told. Let's unpack Newton's bucket. Imagine a bucket filled with water, hanging by a twisted rope. You release the rope. Initially, state I, the bucket and water, are at rest relative to each other, and the water surface is flat. Then, as the rope unwinds, state 3, the bucket spins, creating relative motion between the water and the bucket walls, but the water surface remains flat. Eventually, the bucket stops spinning, state 3, returning to relative rest with the water, but now the water surface is concave, pulled towards the center. The puzzle is this: how do we explain the difference between state I and state 3? Relative motion doesn't seem to be the key, because there's relative motion in state 2, but not in I or 3. Newton's radical answer was that the difference lies in absolute motion, motion relative to space itself. In state I, they are at absolute rest. In state 3, they are in absolute motion. He argued that this absolute space is the real source of the inertial forces causing the water to bulge. It's a profound claim, essentially saying space is a thing, an entity responsible for inertia. Enter Ernst Mach, the empiricist giant, who had a very different take. He didn't dispute the phenomenon Newton described, the tension in the cord, the spinning spheres. Instead, he challenged the phenomenon itself. Mach denied that the spheres would remain separated. He argued that, in truly empty space, the spheres would actually pull together. Why? Because inertia, he believed, doesn't come from absolute space, but from the distribution of matter in the universe, specifically the distant stars. His reasoning was that the tension we feel when swinging a bucket of water is due to the Earth's mass resisting our attempt to accelerate it. Similarly, the sphere's resistance to rotation must be due to the gravitational influence of the distant stars. If correct, Mach's view undermines Newton's entire argument. Newton observed a phenomenon tension despite no direct force pulling them apart, and inferred absolute space. But if Mach is right, that phenomenon wouldn't occur in the first place. This is a fascinating counter-thought experiment. It doesn't argue against the conclusion absolute space exists, but against the premise the spheres would behave that way. This Mach versus Newton exchange highlights a tricky aspect of thought experiments, counter-thought experiments. They're rare and difficult to construct effectively. Why? Because they target the very phenomenon that makes the original thought experiment compelling. Think about Newton's bucket or spheres. We readily accept the initial setup, a bucket of water, a spinning sphere, because it mirrors everyday experiences like twirling a rock on a string. The tension feels real. Mach's challenge was to say, hold on, that feeling of tension, that resistance to rotation. Maybe it's not because of space, but because of the stars. And maybe the spheres wouldn't even show that tension in empty space. It's a direct assault on the stipulated phenomenon. The effectiveness of such counter-arguments is debatable. Did Mach really undermine Newton? But the point is, it forces us to question our assumptions. It reminds us that we can be easily convinced by a persuasive narrative, even if it's based on questionable premises. Starting from the same setup, a skilled thinker can lead us down vastly different paths. This raises a serious concern. How reliable are thought experiments if their conclusions can be so readily challenged by alternative mental scenarios? Thought experiments aren't just about the physical world. They can also probe the nature of evidence and conception itself. Consider Sidney Shoemaker's brilliant thought experiment addressing the idea of time without events, like Newton's absolute time persisting even if nothing happens. Some philosophers argue such a concept is inconceivable. Shoemaker's goal wasn't to prove absolute time exists, but to show it could be conceivable and, more importantly, that we could have reasonable evidence for it. Imagine the universe with 3 planets, A, B, and C, visible to each other. Planet A freezes every 10 years, everything stops, mid-sentence conversations, falling apples, but only on A. Meanwhile, B and C continue normally and observe A's freeze. Since events keep happening on B and C, it's perfectly reasonable to say time passed on A during its freeze. People on A would also agree, noticing the drastic changes in B and C's experience. Now let B freeze every 4 years and C every 5 years. Same logic applies. Now, here's the twist. Every 60 years, the least common multiple of 3, none of the planets freeze. Why? 2 hypotheses. E, all froze simultaneously. Nobody saw it. R, each skipped a freeze cycle. Which is better? Hypothesis is far more plausible. Shoemaker argues this scenario provides a conceivable case where empirical evidence the pattern of freezes and non-freezes, explained by simultaneous global freezes, strongly favors the existence of absolute time passing even during local freezes. It shows time without local events is conceivable and potentially supported by evidence. We've seen lots of examples, positive and negative. But a fundamental question looms large. How is this possible? How can we genuinely learn something new about the physical world, make discoveries, just by thinking through these scenarios? What's the mechanism? This is where different philosophical accounts come in, trying to explain the epistemic power of thought experiments. These accounts often differ sharply on what exactly is going on in our minds when we run one of these mental simulations. Let's look at 2 prominent contenders. First up, John Norton's influential argument view. Norton basically says, let's be empiricists. Let's strip away the fancy metaphysics. His core claim is that thought experiments are nothing more than arguments. They start with some premises, facts, or assumptions we already accept, ideally grounded in empirical experience, and through deductive or inductive reasoning, they lead to a conclusion. The conclusion then inherits the empirical legitimacy of its premises. According to Norton, thought experiments achieve their effect by implicitly setting up and then executing such an argument. He characterizes them as arguments that posit hypothetical situations and use particulars that are irrelevant to the general conclusion, though they might make the argument more vivid. Think of Galileo's example. The premises are the laws of motion and the properties of the balls. The conclusion is about their equal fall rate. The thought experiment guides us through the steps of the argument. The appeal here is its strict adherence to empiricism. It explains the power of thought experiments using only resources an empiricist would accept observation-based premises and logical inference. Now Norton's view sounds neat, but it faces challenges. The obvious objection is, show me a thought experiment that can't be reconstructed as an argument. For a long time, this seemed easy. But Norton, remarkably, has been adept at taking proposed counterexamples and showing how they fit his argument framework. Does this mean thought experiments are just arguments? Not quite. Think about mathematics. Can all math be reduced to set theory? Logically, yes, you can define numbers and prove theorems using sets. But does that mean mathematics is just set theory? Most mathematicians would balk. They work with numbers, functions, calculus directly, not constantly translating everything into set theoretic language. The real success of mathematics comes from manipulating these concepts directly. Similarly, the success of thought experiments might lie in the intuitive, imaginative process itself, not just in the final logical reconstruction. Reducing a thought experiment to an argument might tell us what it amounts to, but it doesn't explain why the original mental process felt insightful or productive in the way it does. Alright, if Norton's view feels too restrictive, what's another possibility? Enter Platonism, championed by thinkers like Alexandre Koyaren, the author himself. This view embraces a kind of traditional rationalism, suggesting that thought experiments tap into a deeper, non-empirical source of knowledge. The argument goes like this. First, consider the laws of nature we use in thought experiments. Are they just summaries of past observation like human regularities? Or are they more like relations between abstract properties, existing independently of our observation? Think Armstrong, Dretske, Thule. Second, consider mathematical Platonism, the idea that mathematical objects and truths exist abstractly, and we have a kind of intuition or perception of them, a view strongly held by Gödel. The leap is then, if we can intuit abstract mathematical entities, perhaps we can also intuit the laws of nature, especially under the special conditions created by a thought experiment. Look at Galileo again. No new data, no logical derivation, just a leap to a new physical principle. This fits the mold of a priori knowledge gained independently of sense experience. Furthermore, proponents argue this view aligns better with the history of science, explaining how figures like Galileo and Newton made their breakthroughs through reasoning and imagination, not just observation and experiment. Of course, Norton and Platonism are just two sides of a much richer debate. There are many other significant contributions. Ernst Mach, with his focus on sensory experience, offered an early empiricist perspective. Thomas Kuhn suggested thought experiments reveal flaws within a prevailing scientific paradigm. Tamar Gendler developed a sophisticated account drawing on Kuhn's ideas. Roy Sorensen has proposed numerous intriguing theses. James McAllister argued thought experiments operate on phenomena, not raw data. Nancy Nersession and Nad Mishkevich independently developed the mental models account, emphasizing how we construct and manipulate internal representations. The field is vibrant and expanding rapidly, with plenty more work to be done. It's clear that understanding thought experiments fully requires grappling with a diverse range of philosophical perspectives. Now, let's shift gears slightly to another crucial concept in the philosophy of science, underdetermination. This is a big deal, popping up not just in science, but throughout analytic philosophy. What does it mean? Simply put, it's the claim that our available evidence, or even all possible evidence we could ever obtain, isn't enough to uniquely determine the truth or falsehood of a scientific theory, or sometimes, a broader class of propositions. We often talk about evidence under determining theories. More formally, we can say a class of propositions C underdetermines another class, CR, if knowing everything in CE doesn't give us enough grounds to know or even be justified in believing anything in CR. Think about the classic brain in a vat scenario. All your sense data CE might perfectly match being a brain in a vat CR, so your data underdetermines your actual situation. Or consider behaviorism. Observing someone's behavior, CE doesn't definitively tell us if they have an inner life, CR. Throughout this discussion, we'll focus on this no, justifiedly believe, underdetermination. Why should we care about underdetermination? Just stating that C1 underdetermines C2 doesn't automatically lead to skepticism. Maybe we have other ways to know about C2 besides going through C1. The real philosophical punch comes when there's an assumed asymmetry. One class of propositions like sense data or behavioral observations seems directly accessible to us, while the other, like the underlying theory or the person's inner state, seems only accessible via the first. Underdetermination arguments typically leverage this perceived difference. They fall into two main camps. First, transcendental arguments, which try to deduce the existence of hidden cognitive mechanisms or rules we use. For instance, arguments in pragmatics claim sentence meaning underdetermines speaker meaning, implying we must use contextual clues and other principles to figure out what someone means. Second, and perhaps more familiar, are skeptical arguments. These argue that because C1 underdetermines C2, and we only access C2 through C1, we cannot truly know or be justified in believing anything about C2. This is the route taken by many anti-realists in the philosophy of science. The most prominent application of underdetermination is in the argument for scientific anti-realism. This argument typically rests on two key premises. First, empirical equivalence, E. For any scientific theory you can name, there exists at least one rival theory that is empirically equivalent to it. What does empirically equivalent mean here? It means the rival theory makes the exact same predictions for any possible observation or experiment. If this holds, then no amount of positive experimental results can ever confirm your theory over its rivals. The data can only ever eliminate theories, never confirm them uniquely. Second, knowledge empiricism, KE. If the data alone don't determine a theory's truth value, then nothing else does either. This premise is quite strong. It essentially says that factors like simplicity, explanatory power, coherence with other theories, the theoretical virtues scientists often cite as signs of truth, are at best pragmatically useful, but don't give us genuine epistemic grounds for believing a theory is true. Put these two together. E tells us theories are underdetermined by data, and KE tells us data is all we have. The conclusion? We can never know the truth value of scientific theories. This leads directly to scientific anti-realism, the view that we should be agnostic about the truth of our best scientific theories. So, how do proponents of underdetermination defend these claims, especially EE? One common strategy is to point to historical examples. They often cite cases like the early versions of Lorentz Fitzgerald Poincaré's ether theory, which were empirically equivalent to Einstein's special relativity before experiments like the Michelson-Morley test ruled out the ether. Or they mention Bohmian mechanics, which is empirically equivalent to standard quantum mechanics but offers a different interpretation. The argument is, if we've seen this happen before, it suggests it's a general feature of scientific theories. However, critics like Loudon and Leplin push back hard. They argue that pointing to a couple of historical instances is hardly sufficient evidence for a universal claim. More fundamentally, they argue that apparent empirical equivalence might be temporary. Our understanding of what counts as observable changes dramatically with technology. What seemed unobservable yesterday becomes observable today. Furthermore, theories only have observational consequences when combined with auxiliary assumptions, background theories, specific experimental setups. As our background assumptions evolve, the observational predictions of theories can change, even if the core theory itself hasn't. So today's empirically equivalent rivals might become distinguishable tomorrow. Another approach to defending EE is formal proof. Philosophers like John Ehrman have attempted to use formal logic and model theory to show that, given certain definitions of empirical equivalence, often tied to shared observational consequences, empirically equivalent rivals must exist for any scientific theory. These proofs are mathematically rigorous within their frameworks. However, they also face challenges. Often, they rely on assumptions that might be controversial, such as the assumption that all scientific theories can be adequately expressed in first-order logic. More fundamentally, the definition of empirical equivalence used in these proofs often assumes a particular confirmation theory, like hypothetical deductivism. But what if we adopt a different confirmation theory, like Bayesianism? From a Bayesian perspective, even if two theories share all observational consequences, they might assign different probabilities to other potential evidence statements. In a purely subjective Bayesian framework, one could even assign prior probability 0 to all empirically equivalent rivals, meaning the data could eventually drive belief towards one theory. So, proofs of EE based on shared observations might not guarantee underdetermination across all conceivable epistemological frameworks. Perhaps a more viable path for an underdetermination argument lies not in demanding actual empirically equivalent rivals, but in arguing that every theory has rivals that are practically indistinguishable from it. Consider theories like string theory. Proponents might argue it's testable in principle, but practically, the energies needed to probe the relevant scales are unimaginably high, far beyond anything foreseeable. Atkinson estimated needing energies 10 to the power of 16 times higher than planned for the LHC at the time. If every scientific theory has such rivals, theories that are distinguishable only by evidence we could never realistically obtain, then doesn't that still pose a serious challenge to scientific realism? Even if we can't construct the rival, the mere possibility of its existence, given practical limits, seems to leave the truth of our current theories forever open to doubt. This weaker claim, practical underdetermination, might be harder to refute than the stronger claim about universal actual empirical equivalence. Okay, so if we accept that theories might be underdetermined by data, how do realists respond? The main thrust is to deny premise KE, the idea that data is all that matters. Realists argue there must be other ways to get epistemic support. A key candidate is inference to the best explanation, IBE. Roughly, the idea is, if you have two theories that both fit the data equally well, you should prefer the one that provides the better explanation of those data. Assuming it's true, this gives explanatory power a role in theory choice, and proponents argue a connection to truth. But defending IBE is notoriously difficult. You can't just say IBE works because it helps us explain successful science. That's circular. It begs the question by assuming IBE is reliable. Attempts to justify IBE via enumerative induction, like saying every successful use of IBE adds support, run into problems, especially concerning unobservables. How do you count successes for things you can't observe? Defending IBE empirically seems to require assuming IBE is already working reliably. A third less common response comes from pragmatism. Pragmatists tackle KE by redefining truth itself. They argue that KE is false because theoretical virtues like simplicity and explanatory power are not just pragmatically useful, but are constitutive of truth. Being a good explanation, having high theoretical virtues, is part of what makes a theory true, alongside fitting the data. So, if two theories are empirically equivalent and tied on theoretical virtues, the pragmatist says they aren't really rivals. They are just different, equally legitimate ways of conceptualizing reality, both potentially true in their own right. Think of Quine or Putnam suggesting we might oscillate between different conceptual schemes for better triangulation on the world. Of course, this approach faces familiar objections associated with pragmatism: worries about relativism, the potential for self-refutation if the pragmatist account of truth itself is subject to similar considerations. So, wrapping up our look at underdetermination, it stands as a formidable challenge, particularly for those who believe science aims to discover true theories about an independent reality. The core anti-realist argument hinges on showing theories are underdetermined by evidence and that nothing else determines truth. Responses abound, attacking the empirical equivalence claim by questioning historical examples, critiquing formal proofs, or invoking practical limits. Others defend the realist position by championing inference to the best explanation or adopting a pragmatic view of truth. The debate remains fiercely contested, underscoring deep and unresolved questions about how we know what we know in science. It's a testament to the enduring philosophical puzzles surrounding the very nature of scientific knowledge.